Imagine a world where electricity flows forever. No heat loss, no wasted energy, no resistance slowing electrons down. You send current through a wire, disconnect the power source, and the current keeps moving indefinitely. This is not science fiction. This is superconductivity. In ordinary conductors like copper, electrical resistance is unavoidable. As electrons move through the metal lattice, they constantly collide with vibrating atoms. Every collision converts part of their energy into heat. That is why power lines warm up, why devices lose efficiency, and why massive amounts of electricity are lost during transmission across long distances. Now, imagine cooling certain materials to extremely low temperatures. As temperature drops, atomic vibrations decrease. Resistance gradually falls. But in some special materials, something dramatic happens at a specific temperature known as the critical temperature. Resistance does not slowly approach zero. It suddenly disappears completely. This sudden transition marks the beginning of the superconducting state. The material is no longer just a very good conductor. It enters a fundamentally different phase of matter governed by quantum mechanics on a macroscopic scale. To understand why resistance vanishes, we must look at how electrons normally behave. In metals, electrons move independently. They repel each other due to their negative charge and scatter when interacting with the crystal lattice. That scattering is what creates resistance. If you like the educational content, please like, subscribe, and share the video with your friends. However, below the critical temperature, electrons begin to behave in a completely unexpected way. Instead of moving independently, they pair up. These electron pairs, known as Cooper pairs, form through subtle interactions with vibrations in the lattice. Although electrons repel each other, the lattice can mediate an indirect attractive interaction between them. Once paired, these electrons no longer behave like individual particles. They form a collective quantum state extending across the entire material. Billions upon billions of Cooper pairs act in synchrony, moving without scattering. Disturbing one pair would require disturbing the entire collective state, which requires energy the system simply does not allow at low temperatures. This is why electrical resistance drops to exactly zero. But superconductivity is not only about zero resistance. It also has a second extraordinary property that proves it is a true new phase of matter. In the next part, we will explore the Meissner effect, magnetic field expulsion, and why superconductors can make magnets float in midair. Superconductivity is not just about perfect conductivity. If that were the only feature, it would still be impressive, but it would not represent a fundamentally new state of matter. The true proof that superconductivity is something deeper lies in a phenomenon called the Meissner effect. When a material becomes superconducting, it actively expels magnetic fields from its interior. This is not a passive consequence of zero resistance. It is an active, defining property of the superconducting phase. In a normal metal, a magnetic field can penetrate the material without much resistance. But when that same material is cooled below its critical temperature and becomes superconducting, something remarkable happens. Surface currents spontaneously form inside the material. These currents generate their own magnetic field that exactly opposes the external one. The result is that the magnetic field inside the superconductor drops to nearly zero. It is as if the material refuses to allow magnetism to exist within it. This expulsion of magnetic fields is what allows magnetic levitation. If you place a small magnet above a cooled superconductor, the magnetic field interactions create a stable force balance. The magnet can float above the surface, suspended in midair. In certain superconductors, particularly Type II superconductors, magnetic field lines penetrate in tiny quantized vortices, allowing the magnet to become locked in space. You can even flip the system upside down, and the magnet remains suspended. This is not illusion or trick photography. It is a macroscopic manifestation of quantum physics. To understand this better, we need to distinguish between two types of superconductors. Type I superconductors completely expel magnetic fields, but only under relatively weak magnetic conditions. Once the magnetic field exceeds a certain critical value, superconductivity collapses. Type 2 superconductors behave differently. They allow partial magnetic penetration in quantized flux tubes while still maintaining zero resistance. These materials can operate under much stronger magnetic fields and are therefore far more useful in practical applications. Because of these properties, superconductors are used to build extremely powerful electromagnets. In medical MRI machines, superconducting coils generate magnetic fields of 1 to 3 Tesla. In advanced research facilities and particle accelerators, fields can exceed 10 Tesla. Without superconductors, producing such fields would require enormous electrical power and would generate immense heat. However, superconductivity comes with strict conditions. Every superconductor has a critical temperature, a critical magnetic field, and a critical current density. Exceed any of these limits, and the superconducting state vanishes instantly. Superconductivity may sound almost magical, but it is governed by strict physical boundaries. A superconductor only exists within a specific set of conditions defined by 3 key parameters: the critical temperature, the critical magnetic field, and the critical current density. Exceed any one of them, and the superconducting state disappears instantly. Let's begin with temperature. Every superconducting material has a critical temperature, often abbreviated as Tc. Above this temperature, the material behaves like an ordinary conductor. Below it, resistance drops abruptly to zero. This transition is not gradual. It is sharp and dramatic. The first discovered superconductor, mercury, becomes superconducting at about 4 Kelvin, which is roughly minus 269 degrees Celsius. That is only a few degrees above absolute zero. Achieving such temperatures requires cooling with liquid helium, which boils at around 4 Kelvin. Liquid helium is expensive and difficult to handle, which limited early superconducting applications. Later discoveries introduced so-called high-temperature superconductors. These materials, often copper oxide ceramics known as cuprates, can become superconducting at temperatures around 90 Kelvin, approximately minus 183 degrees Celsius. While still extremely cold, this temperature can be reached using liquid nitrogen, which boils at 77 Kelvin and is much cheaper than helium. However, temperature is not the only constraint. Each superconductor also has a critical magnetic field. If the external magnetic field becomes too strong, superconductivity collapses. In Type 1 superconductors, this limit is relatively low. In Type 2 superconductors, there are actually 2 critical fields. Between these values, magnetic flux penetrates the material in quantized vortices, while zero electrical resistance is maintained. Beyond the upper critical field, superconductivity vanishes completely. Then there is the critical current density. Even if the temperature is low enough and the magnetic field is acceptable, pushing too much current through the material can destroy the superconducting state. High current generates internal magnetic fields and energy disturbances that can break apart Cooper pairs. In real-world systems, these limits matter enormously. In MRI machines, superconducting magnets typically operate at fields between 1 and 3 Tesla. In advanced research magnets and particle accelerators, fields can exceed 10 Tesla. The superconducting cables in these systems carry thousands of amperes of current while being cooled to temperatures near 4 Kelvin. In facilities like large particle accelerators, superconducting magnets operate at temperatures close to 1 or 2 Kelvin to maintain stability under intense magnetic loads. All of this demonstrates that superconductivity is not infinite power. It is a delicate balance between temperature, magnetic environment, and electrical load. And yet, despite these constraints, superconductors enable technologies that would otherwise be impossible. Now we arrive at the most exciting question in modern condensed matter physics. What would happen if we discovered a superconductor that works at room temperature? Today, even so-called high-temperature superconductors still require extreme cooling. 90 Kelvin is far from everyday conditions. Liquid nitrogen cooling systems are complex, and maintaining ultra-low temperatures adds cost and engineering challenges. That is why superconductors, despite their incredible properties, are not used everywhere. But imagine a material that becomes superconducting at around 20 degrees Celsius under normal atmospheric pressure. No cooling systems, no liquid helium, no cryogenic infrastructure, just a wire that carries current forever without losses. The implications would be enormous. First, electrical power transmission would become radically more efficient. Today, a significant portion of generated electricity is lost as heat during transmission over long distances. With superconducting cables operating at room temperature, those losses would drop to nearly zero. Energy grids could become dramatically more efficient and more stable. Second, electric motors and generators would become smaller and more powerful. Since superconducting coils can carry massive currents without heating, devices could operate at much higher efficiencies and magnetic field strengths. Third, magnetic levitation transport systems could expand significantly. While maglev trains already exist in experimental and limited commercial use, room temperature superconductors would simplify infrastructure and reduce operating costs dramatically. So why don't we have this already? Because achieving superconductivity at room temperature under normal pressure is extremely difficult. In recent years, certain materials have demonstrated superconducting behavior at temperatures exceeding 200 Kelvin. However, these experiments required pressures millions of times higher than atmospheric pressure, conditions achievable only in specialized laboratory equipment. Under normal pressure, no confirmed room temperature superconductor currently exists. The challenge lies in understanding and engineering the interactions that allow Cooper pairs to form without being destroyed by thermal vibrations. At higher temperatures, atomic vibrations become stronger. Those vibrations disrupt the delicate quantum pairing mechanism. Researchers continue exploring unconventional superconductors, hydrogen-rich compounds, novel crystal structures, and entirely new theoretical frameworks. The search is ongoing. From zero electrical resistance to magnetic field expulsion and levitation, superconductors reveal a layer of reality that most people never see, yet which already powers some of the most advanced machines humanity has built.